Welcome to Maths Mastery. I'm Matt Stabenow. Today we'll be going over Unit 1 of Regents Chemistry. To begin, we're going over classification of matter. Matter is anything that has mass and occupies a volume. Matter can be split up into either substances or mixtures. Substances are one singular thing in your sample, while mixtures are a mixture of multiple different substances within your mixture. So substances are broken into either elements or compounds based off the number of elements comprising them. Elements are only made of one element on your periodic table, and they're either monatomic or diatomic. Monatomic means that the atom floats alone in your sample. Examples of monatomic elements are group 18, the noble gases. Because of their stable octet, they are able to float around by themselves. Secondly, elements can float around in pairs, diatomic pairs, where it's two atoms bonded together existing. Your diatomic elements are your Brinkelhoff, your bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Those are all your diatomic elements. You should have those memorized. You should know they float around in pairs. Alright, going over to the other side, we go over our compounds. Compounds are multiple elements chemically bonded together in typically unit pairs. Compounds are either binary or ternary based off the number of elements that comprise them. Binary compounds are comprised of only two different elements. Examples include water, H2O, or CO2, carbon dioxide. Over here, we got ternary compounds. Those are any compounds that are formed of three or more elements, like CH3Cl. That's an example. Now we're going over to mixtures. Mixtures are more than one substance mixed together, and they can be physically separated. We either have heterogeneous or homogeneous mixtures. Heterogeneous mixtures means that you can see the different components within the mixture. An example, a real world example, is chicken noodle soup, where you can see the components like the chicken, carrots, actually in the mixture. On the other end, we have homogeneous mixtures. These are typically solutions where you cannot see the separate components of your mixture. Think about salt water. You can't see the salt in the water, but still a mixture of more than one substance. Alright, this is all our classification of matter, your substances and mixtures. That's all. I cut that. We'll now be going over various methods to separate your components of your mixture. We'll begin with filtering, the most basic of them all. That works by separating out the solid, the immiscible solid, in your solution by just running the liquid through filter paper. It'll just leave your solid behind in the filter paper. Next is distillation. Distillation works by separating your homogeneous mixture of liquids based on differences in boiling point. So say you have a mixture of two liquids and one is more volatile than the other. You could heat up the solution and evaporate out the more volatile liquid and condense it and separate the two. Next is evaporation. Evaporation works by evaporating out the liquid of your aqueous solution, leaving behind your solute. It's very nice. Typically salt. You boil off salt water and you have your remaining salt left over. Next is decantation. Decantation works by separating the liquid from a solution of a liquid and an immiscible solid or liquid. Immiscible means unmixable. Say water and oil, if you mix them together, they won't mix. It'll just be the oil on top of water, and you can pour off the oil to leave behind the water. Or you could separate off your liquid from a solid by the same method. Finally, we're going over chromatography. Chromatography works by separating out the solutes in your mixture based off differences in molecular polarity. It works by your solutes having a different attraction for the stationary phase, like your chromatography paper that you run your solution through. Various various components will separate at different points based off their attraction for the paper, and you can separate and identify based on that variable. Alright, that's all for your Unit 1, methods of separating out your mixtures. Thank you. Alright, we'll now be going over the phases of matter. And matter commonly occupies 3 separate phases of matter. We'll begin with gases. Gases have neither definite shape nor definite volume. As you can see in this diagram, the atoms or molecules of your gas sample will really just spread out and occupy whatever volume it is of their container, and they're really just like spread out and occupy whatever shape your container really takes. Your atoms or molecules are the furthest apart within a sample of gas. They're really just the largest distance compared to your other 3 states. Your examples of gases on the periodic table are your group 18 noble gases. They are all monatomic elements, you should know that, so they float around on their own. And then the other ones are your nitrogen, oxygen, fluorine, chlorine, and hydrogen. These are all Brinkelhoff elements, so you should know that their atoms travel around in pairs. Next, we're going over liquids. Liquids occupy a set volume, but not a set shape. So 2 liters of soda will occupy whatever shape of the glass or container you have it in, but it will always be the same volume, 2 liters. As you can see, the atoms or molecules aren't really floating around, but they're not set in a real definite shape. Kind of closer together than a gas, but they're not as close as a solid most of the time. Finally, we're going over solids. Solids have both definite shape and definite volume. So no matter what you pour, say, a rock into a glass beaker, it will still keep its shape. The atoms or molecules are set in a set crystalline pattern. It's repeating. They're really just held in place because they're so close together, interlocked, touching. Their motion is vibrating. So solids vibrate, liquids kind of shake a little bit and they move around. And gases, they're really just, in an ideal gas, they're moving around in random straight line motion. Solids are all the elements on the periodic table that have not already been listed as either liquid or gas. So that's all it is, phases of matter. We're now talking about intensive versus extensive properties of matter. Intensive properties don't rely on the amount of substance you have. That's really the big difference between these two. Intensive doesn't rely on the amount of substance you have, while extensive does. So extensive is, say, your mass, the mass of your sample, the volume of your sample, or the weight of your sample. That's not universal for, say, a sample of helium. You can have different masses and different volumes depending on the amount of substance you have in your sample. While these, your intensive properties such as density, conductivity, melting point, or boiling point, all of that doesn't matter. You can have a huge salt crystal and it'll have the same melting point as the tiny grains of salt you use when you're cooking. Density will stay the same because it's still mass divided by volume. So the mass of the substance divided by the volume will always give the same result no matter the size. Different mass value also means a different volume value, so your density is also going to change. All right, finally, we'll now talk about physical versus chemical changes. When you're working in the lab with a sample, you should be able to recognize if a change is either physical or chemical. The difference lies in the identity of your sample, whether it's changing what it is, the chemical composition. So say a physical change is a phase change. A phase change is a great example of a physical change. Say ice melting into liquid water, or liquid water evaporating into water vapor. The H2O doesn't change. It's still just H2O. There's no chemical change. It's still the same substance. So it's a physical change. Phase changes are always physical changes. Another example is, say you have a sample of a solid, and you grind it down in a mortar and pestle. You're not changing the chemical composition of the substance. You're just changing its physical form. That's why it's a physical change. Chemical changes, on the other hand, do involve the change of your substance's chemical identity. A good example is a combustion reaction. Say you're burning methane and it goes from CH4 and O2 to H2O and CO2. You have two new chemical substances that came from something else, so that's a chemical change. Evidence of these changes, chemical changes, are color. If you see a change in color in, say, a solution, then you know something went on. Bubbles are another great example. So if you drop a solid in a solution and it starts bubbling and fizzing, that's a good sign that there's gas being produced, and hence there's a chemical change. Smoke, like combustion reaction, putting off soot, good sign. And heat. Heat is a very good sign. So say an exothermic or endothermic reaction. So heat really means if it's putting off heat, or maybe it's taking in heat and it feels colder. Another great example is the formation of a precipitate. That's further units ahead, but it's when, say, you mix two solutions together and a solid precipitates out a solution, an insoluble product. That's another sign that there's a chemical change. So that about wraps up Unit 1. All these different topics are really the foundation and building block upon which the rest of the course is built upon.